Hello, everyone. Welcome to SQL Server 2022 tempdb, the Uncontended, System Page Latch Concurrency Enhancements. My name is David Pless. I'm a Senior SQL Program Manager for Microsoft, covering the SQL Server 2022 release with a particular focus on new storage engine capabilities, as well as some platform and query store improvements, but my primary focus is a storage engine. In this session, we're going to talk primarily about tempdb, but some of the improvements also pertains to user databases. But if you've been a DBA for some time, you've probably had at least one problem with tempdb on some version of SQL Server. So this is going to be a deep dive into tempdb with some history along with some best practices. But before we get started, I want to remind you of a couple of important references to complement this delivery. Okay, the first article I have here is a blog post that reviews some of the content I have for you here today. It touches on some additional references and explains why the tempdb improvements in SQL Server 2022 are so important. So this article is called Improved Scalability with System Page Latch Concurrency Enhancements in SQL Server 2022 Deep Dive. The other reference really gets into what is tempdb, what is stored there, how it is different in Azure SQL, optimizing tempdb performance in SQL Server, memory optimized tempdb metadata, and how to monitor tempdb. And this one's called Optimizing tempdb Performance in SQL Server. Okay, so let's get started. Now, as I said initially, if you have been a DBA for some time, you've probably had at least one problem with tempdb on some version of SQL Server. If you haven't, you may just not be aware that it was building under the surface. I can say this confidently as it's just one of those common pain points in SQL Server. Now, why was it a pain point? Well, usage is one of those reasons, and by this I mean creating temp tables and other user objects. But tempdb is also used internally to split a disk when there isn't enough memory available for a process, or there is a bad estimate somewhere that causes SQL Server to spill to tempdb. The key point is that tempdb is arguably the most important database in your environment for scalability. So what we're going to do is give a high-level overview of what tempdb is, what it does, some history starting with SQL Server 2016, current best practices, and finally the improvements in SQL Server 2022. And we're definitely going to do a demo of the concurrent GAM and SGAM improvements in SQL Server 2022. Let's talk about what makes tempdb so critical for performance, reviewing some key points. First of all, tempdb is a special purpose system database. It's one of 4 system databases. The structure is essentially just like any other user database. As the name suggests, it was designed for temporary storage. Nothing written to tempdb is intended to be persisted. There's one tempdb per SQL Server instance. tempdb is used by every workload for temporary storage, and this is especially true in a heavy OLTP environment, and transactions are minimally logged in tempdb. tempdb is used by all sorts of things that need some scratch space. Temporary query results and results that don't fit into memory and need to spill to disk. And for the most part, tempdb has information that we only need to store for a short period of time, just until we're ready to read it back into memory. tempdb is recreated every time SQL Server is restarted. We create a fresh copy of the tempdb database using the configured settings. There are some differences in tempdb behavior based on its purpose. For example, tempdb transactions, as we said, are minimally logged. So unlike regular user databases, we don't have to do a full recovery going through the redo, undo recovery process. Remember, tempdb is fully recreated from scratch on reboot, so we only log in order to perform a rollback. The main difference is the workload, because with tempdb we are constantly creating and destroying objects such as temp tables. This is especially true in a heavy OLTP environment where you may have many threads doing all kinds of work. And if you are already seeing resource contention on the system, this impact will be amplified. tempdb is used for temporary, non-durable storage where objects are frequently created and destroyed. This is different from most user databases as the schema is mostly fixed. In user databases, you may add and modify data, but you're not commonly and frequently creating and destroying objects, dropping objects, adding and removing columns, and so forth. So for the most part, your schema is relatively stable in a user database. This is not the case in tempdb, where we're constantly seeing the creation and destruction of temporary objects in high concurrency. Changes are constantly happening in tempdb in volume, and this is very common. So tempdb is pivotal for performance for a number of reasons. For example, when data can't fit in memory, we have to spill to disk. And when you hear someone say that, it means we're spilling to tempdb. We're using tempdb for overflow for what should be in memory, and we know this will be naturally slower. So in SQL Server 2022, not only are we making improvements with intelligent query processing to keep more in memory, but we're also improving the general performance of tempdb. Because so much relies on tempdb health, it is important to get SQL Server's tempdb as optimal as possible. So the key points here is it's important for DBAs to optimize tempdb performance. It's important to track and address tempdb bottlenecks, and SQL Server has improved tempdb in every single release, and SQL Server 2022 is no exception. So, what is stored in tempdb? Of course, temp tables go into tempdb. This is usually the first object we think about. So whenever you create a temporary table in a stored procedure or in a regular batch, that is going to go to tempdb. Table variables are also stored in tempdb. Row versions go into tempdb. So if you're using snapshot isolation, read committed snapshot, where every time a row is modified by a specific transaction, the database will store a version of the previously committed image of this row into tempdb. Hash tables. If we have a hash operation, this will spill to tempdb. Work tables that are used for spools and cursors and sorts, temporary large object storage, this all goes into tempdb. Triggers that use the row version store, this will go into tempdb. Online index operations. So if you're maintaining your indexes with the online on keyword, then we're creating temporary shadow copies in tempdb. dbcc checkdb also creates shadow copies in tempdb. So there's a lot. So basically, tempdb will be used for user objects such as a global or local temporary table or index, stored procedures, table variables, table valued functions, and cursors. But we also use tempdb for internal scenarios, such as I mentioned, spills to disk, and as work tables that store intermediate results for spools and sorts. Now, in support, we often get asked, is there any way to know which of these scenarios is going to put the most pressure on tempdb? The answer is that every environment is going to be different because every workload and what is underneath is different. The best approach traditionally was monitoring the system OS waiting task DMV, and in SQL Server 2019, we have some new functions that can help identify the statements causing the pressure. We'll review those functions in a bit. But the best way to find the culprit is active monitoring, and I recommend logging the pressure over time. All right, so let's cover some history of how tempdb has improved over time And then we're going to go back all the way to SQL Server 2000 and roll forward to the current release. For a bit of history of SQL Server and tempdb, let's start with SQL Server 2000. SQL Server 2000 was a game changer, and back at this time, there was a majority of platforms on bare metal. Virtualization was considered a no-go for many environments, and it was largely a 32-bit world on NT4 and Windows 2000. But there was also a time where we started to see some 64-bit machines, but even on these systems, we still had a lot of 32-bit mode applications. We started seeing larger machines, more memory, more processing, and with some non-uniform memory access, NUMA machines started coming out. As we started pushing towards bigger machines with larger workloads, we started seeing concurrency issues emerging in the tempdb space in two key areas. First is object allocation contention, and the other is metadata contention. To address the contention with SQL Server 2000 Service Pack 4, we introduced trace flag 1118, and the support recommendations started to come out to create multiple data files in tempdb. KB article 328551 illustrated at this point, giving us some of the key recommendations that we have. What we're battling here is what was commonly known as object allocation contention. Okay, let's talk about object allocation contention and how object allocation works in your databases. Again, tempdb is structured just like any other database. This will apply to all databases, what we're going to show here, but remember the workloads are different in tempdb. So it just matters more for tempdb because of the constant creation and destruction of objects. So we see on the slide the primary tempdb data file, tempdb.mdf. The table we see under the tempdb.mdf represents pages. Page 0 is a header page, and this is true for any primary or secondary data file in SQL Server. Page 1 is what we call page free space, which is used anytime SQL Server needs to allocate space to an object. Basically, the PFS page contains information on how full the pages are, and for the next 8,088 pages in the database. So if SQL Server needs to add some data, SQL Server uses the page free space page to see how full the associated object is, to see where the data can fit. After 8,088 pages, there's another PFS page in the same data file, so it repeats itself. So you'll have more than one PFS page depending on how large the file is. Page 2 is always the global allocation map, the GAM. And this is where the extent allocation comes in, as the GAM tracks when SQL Server needs to allocate a uniform extent. An extent in SQL Server is comprised of 8K pages, 64K. And this is usually the unit of allocation. So if you have a table that's larger than 8 pages, anytime we allocate space to that table, we will create a full extent. And this is a uniform extent because all 8 pages in that extent belong to that object. So anytime SQL needs to allocate a uniform extent to an object, SQL will go to the GAM and check the availability. The GAM is a bitmap. So if the bit is 1, then that extent is available to be allocated. And if it's 0, then it's not available to be allocated. Once SQL allocates the extent, it flips a bit for that GAM page from 1 to 0 to show that it's no longer available. The larger the file, the more GAM pages you will have. And for the GAM, you will just get another GAM page after 63,904 extents. Page 3 is for the Shared Global Allocation Map, the SGAM. And this page is used if SQL needs to allocate space on a mixed extent. This SGAM page tracks mixed extent usage for when an extent is being used by more than one object. So if I have an object that is less than 8 pages and I don't want to allocate a full extent, we will use a mixed extent. The SGAM is a bitmap. So if the bit is 1, then it's being used as a mixed extent and has space available to be allocated. And then we would look for the corresponding PFS page to find the empty pages within the extent, and then we would allocate that page. The important point here is that the SGAM is used in conjunction with the PFS page in order to allocate space on a mixed extent. And again, after about 64,000 extents, you get another SGAM on the same file. Now, we'll talk more about contention, but since we're here and we're talking about the layout, it's useful to talk about how contention is tracked. When we're looking at the wait resource using SysTM OS waiting tasks, and we're trying to find out what page the latch contention is occurring on, we will find that tempdb is always dbid2. The next number is the file ID, and the last number is the page. So if the last number is 1, then we know it's a PFS page, and so forth. The PFS was commonly a point of contention, but we have reduced that, as we will learn later. Now, when you have multiple files in tempdb, you get another immediate header, PFS, GAM, and SGAM because all files have the same structure. And with multiple files, we try to share the workload over these files. And this is also why we have the best practices that the files should be equally sized, because the way SQL Server spreads out object allocations across the files in the same file group based on the proportional fill algorithm. So that means that we're trying to keep the same percentage of free space in each file within the file group. So if all the files in the file group start at the same size and they stay the same size and they have the same amount of free space, then we turn the proportional fill algorithm into a round robin algorithm, because each subsequent allocation will hit the next file and so on. And this is the reason for the recommendation of having multiple files at the same size, because we're spreading object allocations across the files, and that allows us to get around this object allocation bottleneck. So that recommendation came out in SQL 2000, and it's still true today. Multiple files equally sized is our best practice, and this will stand until testing proves otherwise, even in SQL Server 2022. Now, back in 2000, we would commonly see 2:1:1 and 2:1:3 contention because of how the mixed extent allocations works. This was a common contention point, and this is what brought us to the trace flag 1118 in SQL 2000, which turned off mixed extent usage for data pages. As a result, we don't hit the SGAM contention as much, and that has been largely reduced. Let's talk about another type of contention called metadata contention. When we talk about contention, this is not about I/O. This is contention in memory that happens when there are multiple threads that are trying to modify the same page in memory at the same time. In this case, with metadata contention, multiple threads are trying to modify the same system table at the same time. The tempdb contention here also started back in the SQL 2000 timeframe. So whenever you create an object in a user database or in tempdb, there is metadata that needs to be recorded for that object. So what we're tracking is What are the different types of columns that are in it? What are the different data types in those columns? What is the name of the object? Where is the object located? All these kind of things are stored in these system tables within the database, and there's several system tables, roughly about 12 right now, we have identified that are in critical path that changes over time, because when we add features like column store indexing, in-memory OLTP, when we add all these new features, we also add metadata to support these new features. So over time, the metadata use increases. So around the SQL 2000 timeframe, we started seeing this metadata contention. So what was happening is whenever you have multiple threads all creating a table at the same time, not only can we potentially get object allocation contention that we discussed previously, but we can get contention on the system tables that records the metadata about those temporary objects. And so this also manifests itself as page latch weights, but the numbers will be different. So they're not going to show up as PFS and GAM pages, but they will be other pages that belong to system objects. And this would happen whenever trying to insert into the metadata pages. So at this point, we realize, okay, we've got some contention issues that we really need to resolve in tempdb. So where we know we can use multiple files and trace flag 1118 to help address the object allocation contention we talked about previously. Here, for this metadata contention, there's no configuration option available to help us address this type of metadata contention. Okay, more on that. But next, let's go back down memory lane, and we're going to return to this metadata contention topic. In SQL Server 2005, we had a number of improvements for the SQL Server engine, resulting in many improvements that we still have today. In SQL Server 2005, we introduced temp table caching to get around some of the metadata caching contention. So when you cache a temp table object, when you delete that table, you don't actually drop the metadata. We keep a cache of all the temporary objects that are used through a stored procedure, and then we reuse the metadata for those objects when you call the same stored procedure and use the same temp table again. So with temp table caching, we have fewer hits to the metadata, and we're able to alleviate some of that metadata contention. But in SQL Server 2005, we erased some of this improvement because we started putting more into tempdb. And this is when row versioning came out to support snapshot and read committed snapshot isolation, triggers, and so forth. And table variables came out, increasing the amount we were putting into tempdb into SQL Server. There wasn't much in SQL Server 2012 and 2014, but in SQL Server 2014, what was notable is that we released in-memory OLTP, a feature for high-volume OLTP applications to reduce latching overhead and to improve code efficiencies. In SQL Server 2016, this was a really big release for tempdb improvements. So in SQL Server 2016, the setup itself addressed many of the best practices we recommend rather than forcing DBAs to correct them afterwards. So when there are multiple tempdb data files, all the files auto-grow at the same time and by the same growth rate. And depending on growth settings, all allocations in tempdb will use uniform extents. This means that trace flag 1117 and 1118 are no longer required because it's now the default behavior for tempdb. We also kept seeing this metadata contention even with table caching. So now temp table caching did help for a while, but over time we really needed to do something more to address the metadata contention. So what we introduced is optimistic latching for temp tables in tempdb. So let's revisit the metadata contention topic. In SQL 2000, without temp table caching, we were seeing metadata contention on the insert. Now, with temp table caching in SQL Server 2005, we started to see over time, as concurrency increased, we started seeing metadata contention on the drop or the deletion of temp tables. So when we drop the object, we then have to delete the metadata so we keep it in the cache. So we don't have to delete it normally. But if something gets invalidated in the cache, we then need to pull it out of the cache. And when we do that, we're deleting the metadata. And in order to do that, you have to latch the pages that are part of those tables. And this is where we started seeing the next level of contention. So in SQL Server 2016, we introduced optimistic latching. With the old latching algorithm, the first thing we would do is get an exclusive page latch. So once we obtain this exclusive page latch, then no one else can even read the page, let alone modify the page. So I next scan to see if there's any rows that we need to delete. Now keep in mind that we could have multiple tables and there could be lots of metadata. The more tables you have, the more metadata SQL Server has to scan through. So this can take a long time when you consider that metadata will increase over time. When we introduce new features, we also add new metadata for those features. So this scan will take more and more time over time. So if you're holding that latch for a long time and it's an exclusive latch, so nobody else can either read or write, this becomes your bottleneck. If SQL Server finds no rows, then we can just let go of that exclusive latch. If we do find rows, then we have to delete the metadata for those rows, and only then can we release the latch. So what we've done is we've switched to a new optimistic algorithm. So the first thing we do is acquire a shared page latch. So what we're doing here is we're saying, I'm not sure if I have to delete any metadata. So we can be optimistic. Chances are there's nothing for us to delete. So let me get a shared latch, and then I do the scan to see if the metadata exists. If I find rows, then yes, I need to promote to an exclusive latch. Delete the metadata, and then I can release the exclusive latch. If I don't find any rows, then I can just release a shared latch. And so with a shared latch, I may be preventing people from updating the page, but everybody can at least read it. So this reduces some of the contention on the metadata. So that came out around SQL Server 2016. Okay, so now we fast forward to SQL Server 2017. By this release, we're still seeing a high volume of metadata contention, which is only grown with more processing power of underlying systems and removing the points of contention underneath. What's left was the metadata on the system tables. As a result, more improvements came in the SQL Server 2017 timeframe. So we made some PFS changes to the round-robin algorithms for PFS. We changed the way we do the metadata cleanup to make it asynchronous, and then we further improved the optimistic latching algorithm. So for every release in CU that is shown on the slide, we released a new PFS allocation algorithm. So normally what would happen with the round-robin algorithm is every subsequent allocation would hit a new file. So the first allocation would go to file 1, and then file 2, and then file 3, and then file 4. And the old way would go back to file 1, 2, 3, 4, and would keep doing that until we fill up and switch to the next range of PFS pages. But with this change, we now round robin across all of the PFS pages within the file, not just across the files. So allocation goes back to file 1 at the second PFS range, and then subsequent files and PFS ranges. So what we do is we now round robin across all PFS pages in all the files. So we're not just wrapping across files. We are now round robining within the file as well. So you can add more files and you can make files larger. All of that just adds more PFS pages and reduces the likelihood of PFS contention. And so that was introduced in the cumulative updates and service packs that are shown on the slide. So we had to change the way we clean up metadata because we have the temp table caching. We have all these things to try to reduce this metadata contention, but we keep pushing the bottleneck further out. So here's what we did for the CUs that can be seen on the slide here. First of all, a drop of a temp table becomes a no-op, meaning that we initially do nothing. You might drop a temp table in your stored procedure, and we don't actually drop anything because it's all cached. It's a no-op. We were referring to the cached object here. So because the drop is no longer deleting metadata and it's an in-memory object, we actually have a cached object in memory that tracks all of these temp tables that ties us to that metadata. So just like any other cache in SQL Server, there's a clock hand that sweeps. In the event of memory pressure, the clock hand starts sweeping through the temporary cache and moves things to a deleted list. So we don't delete them right away. We just say, okay, we've got memory pressure. We've got things in cache. We are going to evict from the cache and put them on a deleted list. And then we have a separate process that's going to go and clean up that metadata. This background process fetches one item from the deleted list and then removes the corresponding metadata. It could potentially be deleting hundreds of rows from about the 12 different system tables. So I take one item off the deleted list, one temp table off the deleted list, and then this background process deletes the metadata from the system tables. Then we started getting contention on the delete because a super busy workload with temp tables and a lot of active threads, then a single background thread is not going to keep up. So we enlist helper threads. So basically, any thread that needs to create a temp table actually has to clean up a temp table first. And instead of fetching one from the deleted list and then deleting it from the metadata one at a time, what we did in SQL Server 2017 is we changed this from being one helper thread per core to potentially one helper thread per NUMA node. And then each helper thread fetches 64 objects from the deleted list and deletes those 64 objects from the metadata rather than doing one at a time. So we're batching to 64 deletes at a time, and it's only one helper thread per NUMA node, not all the cores on the system. So this should drastically reduce that contention on those system tables, and this applies to all the versions and releases that are shown on the slide and up. Now, this doesn't correct the problem completely, but as of SQL Server 2017, we still had a pretty severe metadata contention, so the story doesn't end here. Let's talk about the tempdb related enhancements in SQL Server 2019. So the first thing we did was introduce the page cracker that allows you to quickly diagnose contention, making it easy to see what's on the pages we're having contention with, and even if they are metadata pages or not. We have sysdmdb page info, where we used to have to use dbcc page in order to see if you had a page number that was in your wait resource and you weren't sure what was on that page. You'd have to dump out the page and then look at the header and examine it. dbcc page required that if you were an admin and the results were not in a tabular format, so it was hard to script and join with other views. Just was in general difficult to use. So sysdmdb page info lets us analyze the header and see what type of page it is and what objects that page belongs to, which is relevant information here when you're troubleshooting page-related waits. The sys function PageRes cracker can be used with sysdm page info to help pass over the page resource as one of the 4 required fields. Now, we're going to use this up in our upcoming demos, And we have a script that we can leverage that's in one of the blog posts that I had earlier in the session. By taking the load off of tempdb and putting more on the user databases, we started seeing other issues such as waits on PFS in the user database, so we implemented concurrent PFS updates. Remember, in order to update the PFS page, we have to get an update or an exclusive latch. The update latch is usually where you see the contention. So with the concurrent PFS page change, instead of getting a latch, we're able to manage the concurrency at the CPU level using something called an interlocked operation. So what we've done is moved the concurrency management and the synchronization down to a lower level, so no more latch waits. So you should never really see a latch wait in PFS on SQL Server 2019 and above, because we now have concurrent PFS updates, which is on by default. Now, you still need multiple files in SQL Server 2019 and should still follow the best practices. In many cases, and especially under higher concurrent workloads, because we still see the GAM contention and sometimes the SGAM contention. And often the case is that once we've shifted past the PFS contention, which we've solved in SQL Server 2019, we now see this on the GAM and SGAM. Okay, so this is foreshadowing a little bit what we're going to talk about for SQL Server 2022. A couple of features to discuss here are ones that you have to opt in to take advantage of. The first is a tempdb related feature, and this one is, and another one that is indirectly beneficial. So memory optimized metadata tables for tempdb is basically a combination of the in-memory OLTP and the temp table metadata features. We took the system tables and the tempdb system tables, and we moved those into non-durable memory optimized tables. Remember that tempdb is temporary. It's dropped and recreated every time you restart SQL Server. So there was no reason for the metadata to be durable, and we converted those 12 system tables that we talked about before that are involved in object tracking and tempdb into memory optimized non-durable tables. But we don't need a specialized memory optimized file group for tempdb since it is non-durable anyway, and so it's all in memory. No disk is needed, and with the memory optimized tables, there's no latching and no locking, and we're able to massively increase the concurrency against these metadata tables using these lock-free, latch-free data structures. Enabling memory optimized metadata tables does require a restart because we have to configure the Hekaton DLLs. It's a big improvement in 2019, and it will eliminate a lot of the metadata contention. But again, it's something that you need to opt in for. Okay. The indirectly related technology that I was talking about is accelerated database recovery. So this is a recovery-based technology that improves recovery by making transaction rollback nearly instantaneous and recovery very, very fast. It's interesting here because ADR shifts the versioning to a local persisted version store, helping take the pressure off of tempdb. And we've made this even better in SQL Server 2022 as well. So this means row versions will go into the user database instead of tempdb. And as I said, ADR for SQL Server 2022 is even more scalable than ever before. Okay, so now let's talk about our traditional supportability and common best practices. So let's talk about the types of tempdb contention and some solutions. So first, we have object allocation contention, which is contention for the pages that are used to manage space and allocate objects in the database. We discussed this. The way you would go about diagnosing the situation is to look for the page latch weights on the PFS and the GAM pages. You shouldn't see really much SGAM contention anymore because trace flag 1118 is the default behavior. But in SQL Server 2019, you can certainly still see GAM contention. So what's our solution? Create multiple files and follow best practices. Now let's talk about metadata contention. This is the contention on the pages that belong to the system objects that would track temp tables in tempdb. This you would diagnose by again looking for page latch contention, but the weights would be on pages other than the PFS and the GAM pages. So they would be in tempdb, so you're going to start with 2: for the database ID, and you would see the file number, but the last number would have different page numbers, or typically higher page numbers, like 1118 or 121, something like that. So what's the solution? Install the latest cumulative updates, and on SQL Server 2019, opt in for the hackathon improvement, the metadata improvement for tempdb. And lastly, on temp table cache contention, if you suspect you have heavy tempdb usage and you're seeing CMEM thread weights or SOS cache store spin lock weights, then it's a good chance it's tempdb related, but there are other possibilities. But if you see that, the first thing you want to do is make sure you're on the latest updates, as we've addressed many of these over time. If it's still pronounced, then I recommend opening a case with CSS, and you may need to find other ways to reduce your heavy tempdb usage. So the solution here is install the latest cumulative updates, open a case potentially if that doesn't solve for it, and potentially consider reducing heavy tempdb usage. We'll talk about those in the best practices, how to do that, towards the end of this session. Okay, so now let's get into the SQL Server 2022 improvements. In SQL Server 2022, we are addressing another common area of contention by introducing concurrent GAM and SGAM updates similar to the concurrent PFS updates. As you know, we use the global allocation map pages when we're looking for uniform extents, and the shared global allocation map when we're looking for mixed extents in tempdb. And under higher concurrent workloads, we may have GAM contention where many different threads attempt to allocate extents on the same GAM page, and each thread must first wait for another thread to release their update latch before they can obtain the same type of latch to make their changes. So basically, we're all just waiting in line. With the update latch, only one thread can modify the GAM page at a time, leading to contention. And this is the primary reason we still needed multiple data files. Because of this contention, throughput is decreased, and workloads that require many updates to the GAM page will take longer to complete, while the machine's CPU will still be underutilized. This is due to the workload volume and especially the use of repetitive create and drop operations. For the SGAM, though in previous releases we eliminated most of this by using uniform extents as we discussed, we can still have SGAM contention where temp table and table variables try to allocate for mixed extents. This causes contention when many temp tables are created concurrently. And we also use the shared global allocation map when we have to address the index allocation map page for the creation of indexes. So with these improvements, we allow concurrent updates to the GAM and SGAM under a shared latch rather than using the update latch. So this will allow parallel threads to be able to modify the global allocation map page. Now, so a really good question that gets presented a lot, and we've heard this, I've gotten this myself, is if concurrent GAM and concurrent SGAM updates are some of the last areas of contention, do we still need the best practices? It's definitely a good question. The answer is we don't know yet. We will say out of the gate, we're going to continue to recommend the same approach as we have before around the best practices, but we may adjust if we find that it's no longer required. But in that question, an important point should be made that even when we followed the best practices previously, it helped, but did not eliminate the contention. In SQL Server 2022, we are nearly eliminating the remaining contention in many ways. Will it change our best practices? Time and testing is the only way to tell. Okay, so now let's take a look at this improvement in action to see what it looks like comparing SQL Server 2019 to SQL Server 2022. Okay, so I have two virtual machines running. One machine has SQL Server 2019, and the other one has SQL Server 2022 running. I also have two Power BI dashboards, one for 2019, one for SQL Server 2022, and they're both being powered by a Power BI streaming data set. Okay. Now, I have the same workload on SQL Server 2019 as I have on SQL Server 2022. I've been running these workloads roughly about the same amount of time each time I do the execute this demo. Differing workloads, but every time I do that workload, I do one workload on one workload on the other. They match up tightly, and it's roughly the same amount of time, but we're going to see a big difference between the two. We're going to see this illustrated, first of all, and I wanted to do this in particular. Highlight the DMV that we've been talking about using the sys function page res cracker, the sysdm db page info functions, as you see here. This is what you would use in SQL Server 2019 and up. In prior releases to SQL Server 2019, we're still going to tell you to use the sysdm os waiting tasks dynamic management view. In both cases, you're really kind of looking at the wait resource, and you're looking at some data here. So because I've already had this populated, the workload is not running yet, but because this is already populated, I want to kind of hone in on this. So what we're seeing here, okay, a couple of things. First of all, look at the wait resource. Now, the first number is always going to be the database ID. And for tempdb, it's always going to be database ID 2. This second number, this is the file ID. So you know I have many files. I'm probably applying the best practices here. I am. And we see that is on, the pressure's on the 7th file, and we know, based on the number here, 2, this is GAM contention. PFS is 1, GAM is 2, SGAM is 3. So we're going to see that here. So 272 was the wait resource, the pressure here. And I can see that it's also GAM contention by looking at the page type description that we see here. Now, this contention was on SQL Server 2019, and what I'm going to do is now run this live. So we know what we're looking for. We have our DMV, okay? We know what we're going after. Let me go ahead and run this workload, and this is differing workloads, but I do at the same time each time to try to keep them somewhat in sync, somewhat comparable. So I'm going to go ahead and run this workload. And then on 2022, I'm going to do the same thing. Okay, so I'm going to get in here, and I'm going to run this workload here. Okay, so both workloads are now running. I'm going to go to 2019. I'm going to refresh and see, do I see anything different? Okay, so we'll see what we get here. Okay, so still getting GAM contention. This time, I see that almost the same scenario, except this time it's on the 3rd file. Okay, now this is just for this particular workload, heavy GAM contention. What are we seeing though on the other side on SQL Server 2022? So when I run this over here, do I see anything? I restarted this instance pretty much right before I connected to test this out. Let's see what we see. Okay, nothing. And now that the connection has been reestablished, should go much quicker. I'm not seeing any results here at all. But what does the dashboard show? On SQL Server 2019, I'm just getting this wall of contention. 166,000 points of contention. 949 milliseconds, almost a full second of contention. It could be for a number of reasons, GAM, SGAM, but likely GAM. And we're seeing just this, again, a wall of contention. 233, 237, 231, just pretty much just stagnant here. What are we seeing on SQL Server 2022? A blip. I got a blip on the radar, and I can tell you what this is. This is the in-memory metadata option not being applied. This one you have to opt in for. I did not do that on the SQL Server 2019 or the SQL Server 2022 instance, and I can tell you why I didn't do it. I didn't do it because I wanted to have something to populate this dashboard. Otherwise, is your dashboard broken? I'm not seeing anything. On SQL Server 2019, we're seeing heavy amounts of GAM contention, periodic SGAM contention, even though it's much lighter post SQL Server 2016 and other releases. We've definitely resolved the PFS contention in SQL Server 2019 with concurrent PFS updates. We have the ability to opt in for the metadata contention. I see almost nothing here in SQL Server 2022. We've resolved so much of the contention here in SQL Server 2022 that time will tell, but we may have to update our best practices. We may have to change our best practices, our best practice documentation, simply because so much of the contention has been addressed with concurrent PFS updates, and that was 2019, concurrent GAM and SGAM updates in SQL Server 2022. We're going to stay with those best practices until testing shows otherwise, but so much contention has been addressed. Scalability is definitely going to be a big option for you with tempdb and SQL Server 2022. And SQL Server 2019 had already resolved so much, but look at the difference just being able to address these points of contention in the product. Absolutely enjoyed going through this, enjoyed walking through the history and the story of tempdb in SQL Server, and I really look forward to your feedback on SQL Server 2022 and what you were able to encounter around scalability in your own testing. So let's wrap up, and I look forward to your feedback. Thank you so much for joining. So let's take a quick look at our current traditional tempdb best practices. This is really kind of a summary. Now the question is, do we still need the best practices? Now, we're going to go into some patterns and practices and discuss this further. I'll tell you on SQL Server 2022, we're still going to recommend that you apply the best practices. Time is going to tell whether or not we still need to follow these best practices. I'm definitely going to tell you to follow the best practices on prior versions. Continue to do so on SQL Server 2022. It's definitely not going to hurt, but we've solved for so much in SQL Server 2019. We solved for so much in SQL Server 2022. In the meantime, let's talk about patterns and practices for tempdb health. So what are our options for tempdb health and performance? Again, use multiple equally sized files, 1 per core 8, and then increase them as needed. This really comes down to how many threads you have all creating temp objects at the same time. So if you have 128 cores in your system, you probably don't need to create 128 tempdb files. It will come down to if you really have 128 threads all creating temp objects at the same time, and this is causing pressure. It's possible that you do, but most environments, 8 is enough. So start at 8 and monitor and increase as needed. When you increase the files, increase in multiples of 4 and test and monitor. And it's recommended to restart SQL Server soon after you add files due to the sizing and proportional fill algorithm. If you don't restart, your files will not be equally sized, and that'll cause issues, of course, so as we've discussed previously. Enable trace flag 1117 and 1118 if you're on SQL Server 2014 and earlier. Let's talk, we haven't talked about this at this point. Let's talk about code changes just a little bit. So for the metadata contention topic, the important thing is to make sure that we can leverage the temp table cache, and that there are some things that you can do in your code that would cause us to have to invalidate the cache and therefore not be able to reuse. So we don't want to get in that situation where we can't get the benefit of the cache. So there's a couple of things to avoid. First of all, do not alter temp tables after they've been created. So when you create them in a stored procedure and then you put some data in there, and then you want to add an index that will actually invalidate the cache, we can't reuse that temp table from cache. So that usage pattern can lead to increased metadata contention. So what we recommend that you do is you move index creation to inline index creation syntax. This came out in SQL Server 2014 when we introduced in-memory OLTP. We introduced the ability to create indexes in line with the table create statement. So we recommend that you do that. Some people may be concerned that inserting data is slightly slower because you're inserting into a table that has indexes. However, this will not be nearly as impactful as the metadata contention that you're going to get by not being able to leverage temp table caching. So the recommendation is to do the index statements in line. Also, avoid truncating temp tables if possible, because it's a metadata operation. It's just one more thing hitting the metadata. Also, avoid using temp tables inside ad hoc batches, because we can't cache temp tables that are created in an ad hoc batch. We can only cache temp tables that are created in a stored procedure. So if you want to be able to leverage that caching, then you need to be using stored procedures and not in an ad hoc batch if possible. The last point comes down to the version of SQL Server you're using. First, make sure you are on the latest service pack and cumulative updates. It's also recommended to get on the latest version of the product. It's also important to be aware of what's being addressed in each version, and also make sure you know the problem you're solving for. Hence, you must monitor. There's been so much information here. I hope you got a lot out of it. Thank you so much for joining this session and being part of the Data Platform Summit. Thank you again. There's some ways to win some prizes. Post your selfie with a hashtag DPS 2022. Please give your session and conference feedback. It's really important to us. Visit the sponsors and exhibitors